Myself, Parshiv Kapoor. Me and my co-author Yash Bansal would be presenting this poster. This poster presents our work titled Weighted Color Morphology Feature Fusion for Tuberculosis Bacilli Detection from Cytopathology Images. In this work, we focus on improving automated detection of TB bacilli from microscopy images. To start with, as we all know that tuberculosis diagnosis still depends heavily on manual screening of acid bacilli by experts. This is slow, tiring, and extensive, especially in places where TB cases are high. Even though deep learning has been used, most existing methods require large annotated datasets and suffer with high false positive rates. In this work, instead of doing that, we focus on bacterial morphology relevant information through our framework called MorphCharnet. We used 200 ZN stained cytopathology images with 100 TB positive and the other 100 TB negative slides, all expert annotated and collected from AIIMS New Delhi. Patch extraction. The difficulty was that these whole slide images were very large, so we had to divide them into 80 by 80 pixel patches. Positive patches were overlapped with expert annotated bacilli, while negative patches included white regions, staining transitions, dye blobs, and bacteria-like artifacts. This forces the model to learn the difference between true bacilli and confusing false positives. The next step was dataset processing. Each patch is converted into multiple color spaces. We pass every channel through a reconstruction network of a frozen unit and measure how well it can be reconstructed. Based on that, we selected L channel from the HLS space and the SV channel from HSV color space, including their Sobel maps.
We propose a novel framework called MorphCharnet, which first assigns weights to each channel based on the reconstruction error. It indicates how important each channel is for the bacterial morphology. The input is then passed through a lightweight CNN with the spatial and attention blocks with residual connections. It helps the network to focus on small and relevant bacilli structures. Further, to handle severe class imbalance and reduce false alarms, we use a modified focal loss that penalizes false positives more strongly. Finally, we apply GradCam for interpretability. As shown in the results, the GradCam shows that the model consistently activates on real bacilli regions across the whole slides. Our method achieves 99.4% recall and 97.65% accuracy. Further, ablation studies show that each of our model components, the channel selections, the reconstruction guided weighting, attention blocks, and the loss function all contribute to the better performance of our model. We also compare it with other state-of-the-art architectures, and our model consistently outperforms them. To summarize, we present a simple, interpretable framework for tuberculosis bacilli detection. It explicitly focuses on stain invariant and morphology relevant features. Our method generalizes well and can be extended to accurate bacilli localization in future work. Thank you.